that moment. So I'm willing to give you the take-home final. Let me make a decision on Monday. Let's come back, have a read discussion about it all. Your final is on that Tuesday of finals week, whatever date that is.
It's May 9th.
May 9th. So let's think about that, okay? Okay, I wish I talked with you guys regularly, once a week or something like that. And I think I'm gonna do that, so apologies on leaving you out of that experience. I think it would have been good in the long run, but I learned to. So I need that interview. Okay, let's see if we can get through some stats. Before we begin that, what does the article say that the BASP editors wrote? First of all, what does BASP stand for? Basic and Applied Social Psychology. So they made a statement. Tirofew, the editor, he self-cites himself. He says, in whatever year Tirofew said this, Tirofew's writing it. So he's at University of Arizona, is that right? So it did, Arizona State, one of those. Is it? Okay, sorry, Southwest. So, what did he say? No null hypothesis testing. He specifically says the null hypothesis significance testing procedure. What he means is Neyman Pearson. So the null hypothesis significance testing procedure is if P ducks alpha. And I'm going to show you that in the most powerful way you can do that, that's equivalent to if your likelihood ratio statistic ducks some C. And you can calibrate that C to some probability level. There's a one-to-one mapping with all of that. So they say none of that, get rid of it. And that's a bit harsh, because I do think in good experimental designs, a p-value could be meaningful if you've actually controlled everything. But in observational studies, it doesn't work. So if you just crank up n, you'll eventually duck alpha, guaranteed. And so you can prove that. So what's the probability of, how is a p-value distributed if the null hypothesis is true? Let me just ask this question. How is the p-value, and this is the probability of more extreme data, of course you need tail direction, that's determined by the alternative hypothesis, conditional on the null hypothesis being true. So it's the probability of your data and more extreme data given that the null hypothesis is true, or more extremity is defined by the alternative direction. So how is a p-value distributed if H naught is true? Just real quickly, I'm curious. It's uniform, yeah. So the p-value will be uniformly distributed. Proof. There's probably more reasonable proofs for all of this, but I'm just going to say the probability, we're going to have the probability under the null hypothesis. So what that really means is that we're conditioning on theta naught, whatever that is. Theta is equal to theta naught. I'm going to look at my cumulative probability of my data of my test statistic. So the probability of whatever my test statistic is, this is usually given by Neyman Pearson, the test statistic that you work out. So keep in mind for the normal example we looked at, we're going to look at x bar and its deviation from theta naught, and we're going to scale it by sigma over root n. That's the test statistic that fell out. Why do we use that? Soon we'll know that it's the uniformly most powerful thing, that it reduces the type 2 error. It reduces the rejection probability in the alternative region. Lots of ways to say the same thing. So this is the probability of Tx. It's going to be less than, I'll just say some random variable. That's just a number. We know that this is a monotone function. Probabilities add. That's a beautiful thing. So as I add up more and more probabilities, they're cumulative and they add up to 1. So this is a monotone function because it's a probability right here. So I can invert that thing. It's a monotone function. A lot of times we make this like cap f or something like that, or cap f for just the cumulative distribution. So this is just going to be probability of H naught. I'll write it like this, under theta naught. And then I can invert this function right here, so it's the probability that Tx is less than or equal to probability T. Right here. So this is some random variable. Here's a probability statement of it. So this is the probability. Oops, I should have put inverse on there. If you like F inverse, you can write F inverse. So I'll just rewrite it maybe the way that you're used to seeing it. So whatever my test statistic is, this is all my data in here. Neyman and Pearson might give you that test statistic. You could use another one. It might jump up your answer and you wouldn't be as powerful to detect the difference between your stuff and the null. But this is going to look like F inverse T. And this is going to be F theta naught, F inverse T. Question is are those the same F's? And they might be. So this is usually whatever the truth is. This is true theta. So this was the truth over here. So that's under the truth. Remember our cumulative probability distribution is under the truth. We collected data. It's under some theta. Question is that actually theta naught? And so if this actually is theta naught right there, so if that is true, if the truth is theta naught, then those are the same F's. That's equal to T, right there. So I go back here and I look at, oh, the probability of this test statistic being less than T is T. And there's only one distribution in the world that has that property. That the probability of, if I say, what's the probability of less than being 0.7, and I say it's 0.7, and then I induct and I say, what's the probability of being less than happy face, and I say it's happy face for any happy face, that's uniform. That means it's a uniform distribution. So uniform distributions have this cumulative right here. So if this was not the null, that would be the alternative, and this would be an entirely different distribution. It would be decaying towards zero as it got bigger and bigger. So what's the chance of P ducking alpha if the null hypothesis is true? It's alpha. So that's fine. So it's alpha itself, so what's the probability of a type 1 error if the null is true? And I pick alpha to be my rejection region, very typically at 0.05, then the probability of making a type 1 error under the null hypothesis being true is 0.05. So, and it's something different under the alternative. And so what we want to do is we want to minimize that error under the alternative. And that's what Neyman and Pearson is all about. So I've said it a few times that the likelihood ratio test stat does that for you automatically. That's the statement of the Neyman Pearson lemma. And it also says something a little bit stronger, that if there is a test stat that has a level or size alpha, so that's the 0.05 thing, test, if there is a uniformly most powerful test, i.e. it has the lowest type 2 error in all of the alternative region, that's what uniformly most powerful means. Let's just write that down. UMP, uniformly most powerful. It says this, B, and I'm going to say this is my power function, and that's just the probability of rejecting. It's a function of theta, depending on where theta lives. I'm going to say this is my power function for a UMP test. And I'm going to say theta prime is going to live in the alternative region right here. And I'm going to say that this is going to be bigger than b theta. This is going to be the power function for some other test. b theta where theta prime is an element of the alternative space. So it basically says you want the probability of rejecting the null hypothesis in the alternative space to be high. I.e. the probability of rejecting we want to be high in the alternative space because the null is true. So we just want it to be bigger. So what we're going to do is prove this later on. Let me just write down what a power function is real quickly. I'll do a Josiah, just stick it right next to the question itself. So that's okay. It works eventually. So power function is just the probability of x being in a rejection region. So coming up with the Neyman-Pearson lemma will define the rejection region for you. So this is given theta. We'll look at an example in a minute. But that's where we're going with everything. You might think about, does it make sense if the alternative were true, if I put in an theta alpha right in here, what the distribution of this thing would be? And I think that's what people should look at. And they should be forced to do it and say what their p-value should be distributed as if a reasonable alternative is true. What they have to do that calculation is to find a meaningful alternative. People are cowards. So they don't like to do that. They like to make these huge sets. So saying that, you can make a function of that, but I'd like to know what that distribution is. Or if they were distributed differently. If this was just a totally different distribution, I've misspecified this model. So let's say the true distribution is Cauchy, and I use the normal, oopsie daisies. What would the distribution of the p-value be like there? So people don't answer that question. Neyman and Pearson believe that people should answer that question, but then people are just like, it's way easier to just disregard the null hypothesis of p dux alpha and not think about anything else, moving on. So you might not know what you actually rejected if you do that. Is it the hypothesis or your modeling assumption? Okay, let's come back to this example real quickly. And we can just look at likelihood ratio test. We'll attach this to power by looking at a binomial example, then we'll circle back around to what I just told you and formalize a proof. So uniformly most powerful tests satisfy the likelihood ratio tests lead to uniformly most powerful tests. So if there is a uniformly most powerful test, it adheres to the likelihood ratio test. That's Neyman-Pearson. I've heard people say that Neyman-Pearson set back statistics 200 years. I think that that's rather a harsh interpretation. I think what they were trying to do is explain something to Fisher, and it just backfired wildly. So I don't think what Neyman and Pearson did is problematic. I think everything they explained to us is good. They didn't say to use everything the way that we use it today. And I think they were trying to clarify an argument with Fisher. Fisher wanted to think about the p-value maybe is the probability of the null hypothesis being incorrect. And it's just not true. That's not what it is. So the p-value is something you can use to calibrate an error rate if you fix that type 1 error rate in advance and to control error rates. And that's what he was explaining. And Fisher was like, well, this is nonsense because then you have to come up with a strict threshold, blah, 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 blah. And Neyman and Pearson are correct. If you want to use the test that way, then you have to do that in advance. And it doesn't actually matter what the p-value itself was. And you're supposed to be rather strict about this. So you would treat a 0.0499 very differently than a 0.0511. I do a 0.05000001. So that makes it maybe too big. So I sympathize with Fisher that arguing about that point, it must mean we're doing something wrong. Keep saying that. It's obvious that we're doing something wrong. Trouble with this Neyman-Pearson stuff is sometimes it has good properties, and it all depends on what type of hypothesis we're testing. So the one-sided and the simple versus simple stuff I don't think is highly problematic. Keep in mind the likelihood ratio is defined by a one-sided bound, so there's some coherency to that. And maybe I'll make my point in this class about that, but in my base class I spent about a week making that point. The p-values under certain types of alternatives are incoherent, and that's the word that we use, but they just don't make sense. So, but they do control error rate, but they're not measures of how much you believe the null hypothesis. So, very different things. Understanding that is crucial. I think if you are running a conveyor belt and seeing a semi-IID process, and you're doing things over and over again, and you're willing to incur some amount of error in a process, and you're able to tie that to some utility like dollars, like if you have to do a recall on a product, that makes perfect sense to control a process like that. But if you're just going to go out and collect one data set, what does it mean? You don't get to repeat anything. So I'm not sure that's what we should be doing. So that kind of explains the gross problem with repeatability in statistics, is we're applying something that doesn't really fit. Okay, let's go back to this example right here. So our sampling distribution looks like this, f of x given theta. I haven't stated all the boundary conditions, but x is greater than theta, and theta is greater than 0. I guess it could be 0. But to mess with the sign of everything if we let it go negative. So this just looks like this. So theta, boom. And this is a function of x, so it's bounded by theta. The likelihood function looks a little bit different. We wrote this down last time. It's proportional to e to the minus sum. I goes from 1 to n, xi minus theta. I'll put that all in there. So theta is getting summed up n times and everything. That's the likelihood function. And now I want to think about our likelihood ratio test stat. So this is x, and this is going to be the maximum under my null space. Oh, I should probably give us a hypothesis to test. Theta is less than theta naught versus theta greater than theta naught. So just as a prelude, I'm not going to think this is a terrible test. So whatever comes up with it, a Bayesian would probably put a flat prior on a shift parameter, and the Bayesian's posterior probability under that case will probably coincide with the p-value. So I like those sort of things. If I can come across analyses using different lines of attack and they coincide with each other, it makes me feel like I must be doing something right. So you can verify that, but this is going to be theta element to the null space. This is going to be my maximum likelihood estimator down here, likelihood functions. And really, there's just one question right here about this likelihood function. I'll draw it here. Is where is theta naught with respect to the minimum? I need to be even more careful right here. I need to write down that theta is bounded by x1, the minimum. And so I like to encode things in and put them there and not stick them off to the side because I know what to do when I get to a computer. So this looks like this. x1. This is a function of theta. There's my likelihood function. So it truncates right there. So this is an increasing function in theta, and it's bounded by x1. All you have to do is stare at the equation. Negative, negative, that is increasing in theta. So there's your likelihood function. And so if theta naught is over there, then this thing is maximized right here. If theta naught is here, then in the null space it's maximized at theta naught. So let's just look at this one. In the null space, so that's going to be theta is less than theta naught. So if theta naught were here, I can't maximize that here at theta naught because theta naught's not a valid value. And so that indicator is going to turn it off and make it 0. And so that's not a very maximum likelihood value because this likelihood function is actually coming down and being 0 over here. So if theta naught is big right here, we take the maximum to be x1, the minimum. And if theta naught were over here, then I'm going to be bounding the null space over here, and I'd maximize it at theta naught. So this has two different possibilities. Lambda x is going to be equal to 1. I'm going to have the same thing. This thing we know is maximized at x1. That's the maximum likelihood estimator over the entire space. I don't care where theta naught is right here. This is maximized right here. So if theta naught is greater than x1, then the numerator is going to also be maximized at x1. And so when I take the ratio of those two things, I'm going to get 1. So it's when the other thing happens that theta naught is less than x1. I guess you could put in an equal sign. I don't really care because if they are equal to each other, it's going to be one condition. Well, I guess I'll just put in that. Probability 0 stuff. So this is going to look like e to the minus sum of the xi's minus theta naught over e to the minus sum of the xi's minus x1. And I can simplify all of that. So I can write this down is e to the n theta naught minus x1. So that's just a simplification. The sum of the xi's cancel each other. It's not informative about anything. If we did have a scale parameter in there, like a lambda floating out in front, that sum of the xi would have been informative in estimating the scale parameter. But we know that the scale and the range is 1 in this case, so we don't need to estimate it. So this does not involve anything but the sufficient statistic. We already knew that because it's a likelihood function. And they do the right things automatically. They adhere to the right bounds. So what we're going to do is we're going to bound this by c, and we're going to reject if this is true. And I can rewrite this just by taking the log of both sides. So logarithm c, I'll divide by n right here. This is going to be less than theta naught minus x1. And you might not like that. So I might take this theta naught, throw it over here. So subtract off the theta naught, and then I'm going to flip this around because I don't like the floating negative signs. So that's the rejection region. So if x1 is bigger than that, so I probably should have plugged this over here. But we'll live with that. But this is the rejection region. I want to just be clear about this. This is just some number. So what we usually do is we replace this with just some number and say the probability that x1 is bounded by some other number. We'll oftentimes just replace that by some other notation and say maybe this is like k or whatever. I'll just make it up. So any constants I have in here I could just replace. So the rejection region would be calibrated by looking at what's the probability of x1 being bigger than some number. If you wanted to control the type 1 error rate, what you would do is you would say the probability of x1 greater than some number k, given the null hypothesis. So theta element to the null hypothesis, I might want this to be bounded by alpha. So keep in mind, there's a lot of thetas in the null hypothesis. So I might look at the maximum error rate right there. So I'm going to bound that by this. So this is the maximum type 1 error. So I'm going to look at thetas in the null set. Theta goes up to theta naught, and I'm going to see where the maximum is. I can tell you it's going to occur at the boundary because of the likelihood shape. I'll let you think about that. But that's the name of the game. That's how you actually do one of these calculations. And you can probably account for n. How big does n need to be for the power to be lower? So I might calibrate this, pick my k, and then say at a specified value of the alternative hypothesis, I might be able to use n here and decide how many samples I need to bring down the power, or bring up the power, bring down the type 2 error rate in the alternative space. So that's kind of the procedure that a lot of people follow. Saying that, I always see people do the power calculation if they weren't able to reject a null. They usually say, well, n should have been bigger. Give me more money. They can play that game until p is under alpha. Is it science? Yeah. Got to be much more conscientious about what n and why. Okay, so we've defined what a power function is. It's the probability of being in a rejection region. Let's look at an example. This example is in the book. There's lots of examples. It wouldn't be surprising if I asked you to draw the power curve or something for a normal one-sided example or something like that. We do have to talk about the sharp test. There is no unbiased test for that. So what they do is they take the Neyman Pearson lemma and they do something to it. They do a constraint to it. And then they say it has all the same properties, and it does in terms of error rates, but it becomes incoherent when you do that. That's what Bayesians are usually arguing about. Bayesians do not have a good default solution to this sharp test, but they have a paradigm that I think is meaningful. How you follow it in practice, cowards can't do it. So I'll say more about that later. You have to be specific about your alternative. Binomial example. X is going to come from a bino. N is 5. And I'm going to say my probability is theta. So theta lives between 0 and 1. So you could include boundaries if you wanted to. I usually just don't think it's a real question if it includes the boundaries. So if it's 0, 0, and all we ever see is zeros, and that's all we ever see, we won't know for sure that 1 can arise, but if it never happens for us. Probably our estimate's going to be pretty close to 0. Okay, X is binomial, 5 samples. Let's just consider an example where the rejection region let me just ask real quickly. Let's come up with a hypothesis first. H naught theta less than or equal to a half versus theta is greater than a half. Just intuitively, what would you pick the rejection region to be? Which x's would you reject that null hypothesis? I do get it. It's 9:48 in the morning. The half is a good indicator. 4, 5, 6, something like that. Oh yeah. So 4, 5. What about 3? What about 0? How many possible numbers could x be? So what would you pick? You'd pick 4 and 5? 4 and 5. Anybody pick anything different? I might pick it from 3, and we'll look at why. So simply because half of the observations can be greater than 3 and half less than 3, not including 3. And so that's the break point for this to be a half. So let's just look at we're really conservative, and we do something sensible. Let's say x is equal to 5 is our rejection region. So that's what I reject. So that's R right here. So I'm going to look at the probability that x is equal to 5. Let me just ask a question. Would the test make any sense if I rejected if x was 1? Good. I like that. A good stop. No, it'd be horribly biased. You'd be doing exactly the wrong thing. So bias test is such that the power should be greater in the alternative space than it is in the null space. The probability of rejecting should be higher in the alternative than in the null. So that's what we want. And so if we let x be equal to 1, the probability of rejecting would be higher in the null space than it is in the alternative space. And that would do exactly the wrong thing. I'll let you think about that. So this is sensible, but it's rather stringent. So p theta is our power function. This is just the probability that x is equal to 5. Given theta, I can't help myself, I need to write that down. So probability x is equal to 5, right there, and I know how to calculate this. There's only one way to do it. It's 5 choose 5, theta to the 5, 1 minus theta, 5 minus 5. And it's easier to just write this is theta to the 5. So that's just that binomial probability. Theta to the 5, and we could draw this curve right here. So this looks like this. This is 1. This is 0. So this 1/2 defines my two spaces. This is h naught over here. This is h alpha. And you could draw a curve that looks something like that. The point is rather small in the whole null region. I guess that's good. Maybe. Do we want a small? We want a big. So probability of rejecting, no. One small. Hard to say. How small is small? So I can make it real small. So make it so that I never reject, or something like that. X needs to be 6, I'll never do it. So this number right here, if I draw a line, that's about 0.03. 1, 2. So I just took a half and I raised it to the 5th power. That's the maximum type 1 error rate. That's the size of the test. The level of the test would concern all of this stuff. It's bounded by that. So it can never get bigger. So the book uses two different definitions, level and size. And when we go through the Neyman and Pearson lemma, I'll distinguish those two things for you, but it really doesn't matter. What they're saying is rather obvious. We could just take size to be the maximum of the null set. So this is the size of the test. I'll tell you more about why they talk about the level of the test, the bounding of everything, where they would say the probability in the null space is less than that. I'll say more about that in the proof. It is true what they're saying, it's just kind of meaningless. So, but size of the test, maximum of the type 1 error rate in the null space. So, what if I wanted to talk about the probability right here of a type 2 error at 1/2 plus epsilon? So the probability of a type 2 error right at that point, if I'm just 1/2 plus epsilon, it's going to be about 1 minus that. So complement. So it's going to be about 97%. So the power of the test in the alternative space can be about 97% right there. So that means that the power, 1 minus that is the type 2 error rate. And the type 2 error rate is really high. So let me say it again. The power of the test is this. It's about 0.03. The type 2 error is 1 minus that. That's what I meant to say. That's about 0.97. So that's extraordinarily high, the type 2 error. So there's a trade-off, just like everything. So if I wanted to figure out what theta needed to be for this to be at least 1/2, right here, this would have to be extraordinarily big. So that number we would look at is 1 minus 1/2 theta theta to the 5 is going to be bounded by this thing right here. So we would look at this at that point. So this is just going to be, theta is going to have to be 1/2. This is the type 2 error rate. 1 minus that is the power. That's the power function. So this is going to be 1/2 to the 5th. That's about 0.87. This picture is in your book. So I need to be about 0.87 for theta to be there to have a probability of rejecting the null hypothesis when the alternative is true to be at least 1/2. So this is just too stringent of a criterion. You'll make a mistake on one side less often than the other, but you're just making one of the mistakes too often. So this is the thing I always think about when I'm in a dilemma. I know I'm about to make a mistake. So I question which error is more important to me. So when I think about the midterm or the final exam in giving it to you all as a take-home, I think about the two different types of mistakes. The lazy bad student, whatever, is going to abuse that. And they're going to show up to a qualifying exam and do poorly. So a very good student that takes it for what it's worth, does all of their studying, does everything the same way that they would, are very diligent, aren't stressed out and very relaxed, will do good things with that, no error. So which error do I care about? I don't like penalizing really good students and being like, you guys are terrible, that sort of thing. So it doesn't mean, it's like, oh, no, I don't want to make that error. That's the worst kind of error, because I want to keep you guys encouraged. So do you believe that has a lot to do with a lot? So just think about that. We'll talk about it more on Monday and make our decision. Let's think about what if we had x is equal to 3, 4, 5. So this is a different rejection region. And the power function for it is the probability of either being x is one of these three things, 3, 4, 5. This is just going to be 5 choose 3 times theta to the 3, 1 minus theta to the 2, plus 5 choose 2, 5 choose 4. Theta to the 4, 1 minus theta to the 1, plus theta to the 5. This was the power function for the last one. I'll just simplify it. So that's what that looks like. And we can draw this thing as a function of theta. And it looks like this. It actually goes right through 1/2. You could check these numbers that theta is equal to 1/2. So this is going to be 5 choose 3 plus 5 choose 4 plus 5, well, plus 1, 5 choose 5, right here. So times 1/2 to the 5. Keep in mind that's a half, they're all 5s. Right here. You can work out all of these real easily. So work through all of those right there. 5 choose 4, 5 choose 5, and this will be 1/2. This will be 16 on the top. You can add them up. This will be 32 on the bottom. So that's 1/2. That's why maybe we want 3, 4, 5, because we're going to be able to treat everything at this halfway point, which kind of makes sense, is the separator between them. They have equal probabilities, but you would have to decide how you thought about those two errors, because they're not often balanced. That making one error is maybe more important than making another error. So for example, my spam filter. So how big of a deal is it if I miss somebody's email that's emailing me and needs a signature real quickly? It could be a problem. So how big of a deal is it that I get too many old men advertisements? It hurts my feelings, but I guess I'll be okay. Anyway, with that said, we'll come back next time You know what power curves are. There's a few problems you can work through. I think we have homeworks due today. No, not today? Oh, I put them in the test too? What's that?
Homework's Monday.
Oh, Monday. Okay, cool. We'll have to hustle. Think that's a problem, Jalen? Do you think we'll be able to grade them? If they turn them in on Monday, would we be able to get them back to them on Wednesday?
On Monday?
Yeah, okay. Jay, you're awesome. Cool. All right, that sounds good. Thanks, you guys. We'll come back next time, go through Neyman, Pearson, we'll go through the proof, and then I'll talk about any repercussions and where big Bayesian, non-Bayesian disagreements are. We'll cap things off with that. If you want to know more, I'll tell you what you want. Thanks, y'all. Have a good week.